Hi guys, this is Mrs. Scott. Here's your bad joke of the day. What do you call a cat that breaks the rules? Well, that's a cheetah. Kind of sounds like a cheater. Yeah, that one's pretty bad. But in any case, let's move on to the notes. So your essential question for today, I know it's not shown on here, but we are going to answer the question, how can you show that two lines cut by a transversal are parallel? So it's very similar to what we learned back in lesson 3.2, but now things are just going to be reversed. So if you notice here, we have postulate 16 is actually what we call the converse to postulate 15 in section 3.2. So corresponding angles converse means that we're actually going to start with the fact that we know that angle 1 is congruent to angle 2. So if that's true, if angle 1 is congruent to angle 2, then guess what's true about lines A and B? Well, it's true that line A is parallel to line B. All right, and that works for a few other angle pairs as well. So the alternate interior angles converse is the opposite to theorem 3.1 back in lesson 3.2. So this says if we know angle 1 and angle 2 are congruent, so if angle 1 is congruent to angle 2, then once again, we can say that A is parallel to B. Okay, same thing also holds true for alternate exterior angles converse. So if we know that these alternate exterior angles, angle 1 and angle 2, are congruent, then once again, line A is parallel to line B. And last but not least, this one's going to be a little bit different, but the consecutive interior angles converse. Now again, consecutive interior angles, there's no way that those are the same because one is obtuse, 2 is acute. So this one tells us that if the measure of angle 1 plus the measure of angle 2 is 180 degrees, then we can say A is parallel to B. So this is the only case when we don't say that they're equal, but we say that they add up to 180. Because this consecutive interior angles are kind of the odd ones. They don't equal each other, but they do add up to 180. All right, so we're going to look at some examples here. The first one deals with just figuring out if these lines are parallel. Well, if P and Q are parallel, that would mean this angle would have to be the same number of degrees as this angle. And if I add these two acute angles together, that tells me this is 122 degrees. Well, this one is 120 degrees, so that's not going to be giving us parallel lines because the corresponding angles are not congruent. So they cannot be equal if they're not congruent. Okay, let's look at number 2. So with this one, we have 58 degrees and we have 122 degrees. So these ones we don't expect to be equal because they're consecutive interior angles, but let's see what they add up to. If I add that 122 to the 58, that gives me 180 degrees. So yes, they are parallel. P is parallel to Q by that last theorem. theorem 3.6 told us that if the consecutive interiors add up to 180, they have to be parallel lines. Okay, let's look at a couple more examples here. So moving on with example 3, we're going to answer this question. What value of x would make these two lines parallel? Well, we know that if we can make sure that these consecutive interior angles add up to 180, then line M has to be parallel to line N. So let's go ahead and do that. We're going to add 80 plus x minus 15, and that has to equal 180 degrees. So let's combine like terms. We end up with 65 plus x equals 180. We need to subtract that 65 from both sides, which is going to give us x is 115. And once we have x by itself, we are done. Okay, the next example is going to switch gears a little bit because notice we have corresponding angles. And if we can make those congruent, we know that line M and N would have to be parallel. So let's go ahead and set 5x plus 23 equal to 7x plus 13. And I'm going to start by subtracting the 5x from both sides. So these cancel. We end up with 23 equals 2x plus 13. So let's go ahead and subtract that 13 to the other side. And we get 10 is 2x. Let's divide by 2, and we get 5 for x. Okay. Let's move on to the next page here. So this is going to be a little bit of a proof. We're going to complete this logical argument if G is parallel to H and 1 is congruent to 2, then P is parallel to R. Well, if you notice here, we're given two things. The if part gives you this, and it gives you this. The then part is what we're trying to prove. So notice that's the last statement. We're trying to prove that this line P is parallel to R. Okay, so let's take a look at what we know. We were given that line G is parallel to H. Notice they have little arrows on here showing that. So if G and H are parallel, then why can we say angle 1 is congruent to angle 3? Well, what kind of angles are those? They're corresponding angles. So we know that corresponding angles are congruent if the lines are parallel, and they are. All right, we were also given that angle 1 is congruent to angle 2. All right, well now let's see what we got. If 1 is congruent to 3 and 1 is congruent to 2, we can say 2 is congruent to 3. That is that transitive property of equality. All right, and the last part, now we know from statement 5 that 2 is congruent to 3. So you remember what kind of angles these are? 2 and 3. If we just look at this half of the diagram, so right here, 2 and 3 are actually alternate exterior angles. So remember, if we know the alternate exterior angles are congruent, then the lines are parallel. That is theorem 3.5. If you look at this, this says if angle 1 is congruent to angle 2, then those two lines are parallel. Well, we showed that the alternate exterior angles are congruent, so we know P is parallel to R. Okay, let's look at just one more idea here. There is actually a transitive property for lines, and what that states is that if you know line A is parallel to line B, so say that this is parallel to this, and this line B is parallel to this line C, So if B is parallel to C, then A has to be parallel to C. So they all have to be parallel. So that kind of shows you that you're cutting out the middleman and just setting the first line parallel to the last line. All right, so let's look at one more example here. We're going to explain why pairs of numbered roads are going to be parallel to each other in this section of Denver, Colorado. So this is just a street map of Denver. Let's look at Street 20 and 19th Street. Okay, so here's 19th Street, here's 20th Street. Looks like we have some corresponding angles. So remember, corresponding angles are congruent, then the lines are parallel. If you look back at our postulates and theorems, that is postulate 16, corresponding angles. So postulate 16 tells us that. All right, next we have why is 19th Street parallel to 18th Street? So here's 19th Street. Here is 18th Street. And for that one, it looks like we have alternate exterior angles are congruent. So if the alternate exterior angles are congruent, then the lines are parallel. That's theorem 3.5. Okay, let's look at part C. Why is 18th parallel to 17th? Well, it appears that in this picture, we have the two angles are inside. They're on opposite sides of the transversal, so that's alternate interior angles. So if alternate interior angles are congruent, then A is parallel to B. That is coming from theorem 3.4. So that is the reason we can say 17th and 18th streets are parallel. And lastly, now notice that we know 19th is parallel, or 20th and 19th are parallel, 19th and 18th are parallel, 18th and 17th are parallel. So why could we conclude that they're all parallel to each other? Well, that's what we just talked about up above. That's theorem 3.7, the transitive property of parallel lines. Okay, thank you guys for watching. Again, come see me if you have any questions, or you can comment below, and we'll see you guys soon.